Howdy folks, Mr. Reed here, and welcome to one more question. So what I'm going to be taking a look at right now is trying to, I guess it's solving trig equations, but it's really a very basic sort of trig equation. So I'm just going to have some trig ratios set equal to some value, and we're going to be solving them for either all angles in the entire real number system, or maybe over a specified domain. Usually that's defined by some sort of nice rotation set, as we'll see in the example that I have. So if you want to see solving some really basic trig equations so we can get started on the right path, you're in the right place. Let's get to it. Okay, so I have a couple questions up above. They're fairly similar in a way, but also the expectations of how the answers kind of show up in both cases are a little bit different. So for the first one, we're going to be doing it in degrees, and we have a reciprocal trig function of cosecant theta is equal to negative 2 root 3 over 3. Now, if I have a calculator sitting beside me, and if I have a calculator during an assessment like this, it's really tempting to just grab it and see what we can do with it. However, an assessment, I'm not actually doing an assessment, but anyway, whatever. So the idea here is that I could grab the calculator, I could get it to give me an answer, and that'd be fine, I guess. But I get suspicious of this one. So I see the root 3 and the 2 and the 3 that are involved here, and I think that looks a lot like some of the ratios I get with special angles. That being the case, I don't actually know, really, off by heart, what the special ratios would be for my reciprocal trig functions, like cosecant. What I do know is that the cosecant is the same thing as 1 over the sine of theta. So I'm going to write that instead. Now, for my next step, I'm going to do something that actually I find a lot of my students don't seem to really know is something that's allowed. It's funny because most of the time I complain about them trying things that are definitely not allowed in terms of algebraic methods. But in this case, this is something I see not very many people use. I'm going to actually take my two sides of my equation and I'm going to do the reciprocal of each side. Because as long as neither side is 0 to begin with, or has the potential of having a divide by 0 thing going on right now, this should be entirely fine and won't do anything fishy in terms of our answers. So I'm pretty sure that something that has a ratio of this particular number over here that has nothing to do with 0 at all. So I feel good about this. Going to do the reciprocal of both sides and get that sine theta is equal to negative 3 over 2 root 3. Now you'll notice something kind of weird. My negative sign floats around a lot when I do algebra because I understand that a negative sign out front, which is how it is up there, is the same thing as having a single negative sign in the numerator or a single negative sign in the denominator instead. So I usually tuck it in with the numerator is kind of my habit. So that's why it's there. I'm going to multiply by root 3 both numerator and denominator because I want to rationalize this statement as best I can. So this would be negative 3 root 3 over 2 times 3 now, because root 3 times root 3 gives us 3. So the 3 that's in the numerator is a factor and the denominator is a factor will cancel. And I'm left with negative root 3 over 2. All right, so this is kind of important because root 3 over 2, that is definitely one of our special angle ratios for the sine of theta. Great. So first of all, let's talk about where these answers would exist. And this is probably the part of this process that I like people to try to make as a part of a common sense sort of thing more than anything else. So if you have bought into the idea that cosine theta is the x value around the outside of your unit circle, and sine theta is the y value, then we have a negative y value here. Where does that happen? Well, that happens anytime where we're below the y-axis. So we're looking at, if we label the quadrants 1, 2, 3, and 4, we're looking at a Q3 or Q4 answer. Actually, if we think about the unit circle and where this would occur, it's going to occur twice. So we're actually going to get something that is a Q3 answer and something that is also a Q4 answer. So if you were doing this on your calculator would tell you one of these values. Typically, if it's positive, then it will give you the value in Q1 or Q2 if it can. If it is something that's, not a positive, but if it is something that can be described as either a Q1 or a Q2 positive rotation, it will do that. It will do Q4 negative rotations too. I think most calculators do Q3 as a negative rotation as well, but I could be wrong with that one. Now, what we're going to do in this case, though, is I'm just going to use the fact that I have memorized this. So this is as the reference angle, because I only remember Q1 stuff, like as the things I can pull out quickly. So for sine of theta, the ratio for what are we doing? Degrees. So 30 degrees would be 1/2, and 60 degrees would be √3/2. So in my head, what I'm thinking is I have a reference angle of 60 degrees, and that gives me √3/2. So I need to take that reference angle and place it down into either this or this quadrant. If you're not sure what I mean by a reference angle, you probably want to look that up, because it is a pretty nice concept. What it does is it keeps your symmetry correct, so that the sine and the cosine ratios for all of your reference angle I guess locations. So we could be talking about the angle that's like this all the way around, or like this all the way around. And in either one of those cases, the reference angle is still 60, which means we're going to get this √3/2. The only thing that will change is the potential sign there. So I'll just back that up. And so I have two options. I have 60 degrees past 180, so that would be 240 degrees. As well, I have 60 degrees short of a full rotation, which would be 60 degrees less than 360, which gives me my 300. Now, for these two angles, it's not just the angle that I've written down that's a possibility. Any full rotation will land me on the same terminal arm. We call these things coterminal angles. All coterminal angles have the exact same set of 3 primary trig ratios and 3 reciprocal trig ratios. So all those will be the same. Because of that, we would like to include all of those rotations in our answer. The way I typically do that is by adding full rotations. So 360 degrees is a full rotation in degrees, and I multiply it by some k. And I want that k to represent only full rotations. Positive rotations are fine, negative rotations are also fine. So I'm going to make k have to follow the, I guess, rule that it has to be an integer. So for me, I do k is an element of, that's what that little epsilon is, and that's a blackboard bold Z. I don't know why I do that. I think I was taught somewhere along the way that if we're talking about number systems, it should be a bolded letter, but in order to do a bolded letter, handwriting-wise, a lot of times we do kind of this fake bold by putting a second line on the parts that are kind of vertical. So my diagonal that goes vertical as well as horizontal gets a second line there. So that's my KEZ, or k is an element of integers. If you use I for integers, that's fine. If you choose a letter other than k, that's not really important either. So if you've actually, even the textbook that I use, I believe, uses n, where n is an element of I, and so it's totally different from what I like to go with. Anyway, this is the full set of solutions for this particular problem. So what we end up seeing in this case is that we have 2 lines of solutions. Now, some of you out there might be pretty have a good idea that you could represent both of these lines using a single statement. And so you might say, oh, but what if I said we go around to 270 and then I go 30 degrees more than 270, 30 degrees less than 270. So it's like 270 plus or minus 30 degrees, and then you're going to add on full rotations to that. That would be fine, and you definitely can do that in that manner. Actually, it's probably a little more condensed anyway in the long run. I typically don't care when I'm teaching whether you do it as separate statements or the whole thing. All I really care about is you're able to name all of the infinite possibilities of answers in what's really amounts to 2 separate lines of solutions, each starting from one of the 2 quadrants that are acceptable in this case. So as I said, this is kind of a beginner entry-level trig equation, because in the beginning, all we have is some trig ratio equal to just a nice numerical value. There's no rearranging. We're just going right at it to get our answer. So that's the first one. We might as well go ahead and see what's going on with this second one. So what we're going to do here is we have the tan of theta, is equal to negative 5. And we're going to evaluate this also for theta, but we're going to do it for radians, and there's going to be a specified domain. So that specified domain is a really common one. This is one full positive rotation. So we're allowing all values between 0 and 2 pi. All right, now what we'd like to do with this then is realize that I don't have any clue what special angle might be equal to negative 5 for the value of the tan. So I'm going to assume I just don't know this, which is probably safe. So I'm going to pull out a calculator, actually. I try to avoid this as much as I can, but I'm not going to be able to avoid it here. I don't have pages and pages of trig ratios memorized, so we're just going to go with being able to do this on my calculator. So one of the things that's really important is that I recognize what kind of angle that I would like to have my answer reported in, so I can save myself having to convert it afterwards. In this case, I'm told that I want all values of theta in radians. So make sure my calculator's set in radians, which it is, because I did that before I started doing this video. So I'm good. I'm set in radians, and what we really are doing is saying I want to undo the tangent function that is acting on the angle right now. The way that we do that is by using the inverse function. So luckily, my calculator has built into it inverse trig functions for tan, sine, and cosine. So I can use, in my case, shift, sine, cosine, and tan in order to use the inverse function. So the inverse applying on a normal function, the whole reason why it's the inverse is because it undoes that function. So we'd be left with just theta. On the right-hand side of my equation, that's where my calculator is going to do the tough work for me. So I'm going to put in second function tan for inverse tan, and I'm going to apply that on negative 5. And we'll press equals, and I'll write this down to, I don't know, I didn't have it in the question specified how many digits I wanted for precision in my angle answer in the end. I'm going to take up to this place for no real good reason. Okay, so this is the angle is equal to negative 1.373, and this would be measured in radians. Now, radians are actually a unitless measure, if you've seen me talk about that before. If not, don't really worry about it, but you can put the word radians next to it just to make sure we're understanding what that means. All right, now, calculator's good, but it gives me one answer. Now, that answer is actually in quadrant 4. This is a skill that definitely doesn't hurt to be a little bit comfortable with, because it's knowing which quadrant radian measures are in is not immediately apparent. If we're working in degrees, most people are really snappy on 90, 180, 270, 360. So if we did a little conversion of that, we would have 0, and then we'd have pi, which is about 3.14. And then if we said half of that, ends up being about 1.57. And then if we added that to that other value, we would get, what is it, 4.7, 1, I guess it is, isn't it? 7.1. It may be with some decimal values. I don't know. It might round to 7.2. I had a number in my head, but I think it's actually closer to 7.05. So 4.71 we'll put. This kind of gives me an idea of roughly how big angles are in radians. So when I see negative 1.373, that's actually not quite all the way up to, now I'm going the wrong way for the negative, but it's not all the way up to 1.57. So I'm rotating in this direction, but not quite a full amount of rotation to get to that, I want to say 90 degrees, but the coordinate axis that's down towards the negative y. So this thing right here is the angle that the calculator gave us. Great. Thing number 1, that's not even in our domain, so it's garbage and we don't want to use it in our final answer. Well, not complete garbage though, because we can talk about rotations of that. Thing number 2, it is not the only place on the unit circle where this would be a true statement. So the fact that tan theta is equal to negative 5. So again, tan's a little bit trickier because for cosine, you talk about your x's being either positive or negative, or your y's being positive or negative. Tan is negative when either one of the two sine or cosine is negative and the other one is positive. So in this quadrant down here, the one where we got the answer, my x is positive, but my y is negative, and that's why that quadrant ticks the boxes for what we're looking for. If we were up in this quadrant up here, quadrant 2, that would have a negative x, but a positive y. So that is also going to be a negative tan as well. Some people will use what I call the cast rule, and it's a really good little memory tool. It doesn't have much understanding really in it, but it's great if all you're looking for is to get the sign correct when talking about cosine, sine, and tan ratios. So in this case, only cosine's positive in this quadrant. All of the three ratios are positive in this quadrant. Only sine is positive in this quadrant, and only tan is positive in that quadrant. So it's pretty helpful that way, actually. But I like thinking about the actual XY location, so that's why I talked my way through it the other way the first time. So we're looking for an angle that is over here hanging out in quadrant 2. One of the things is that this angle has to have the same reference angle as this one over here. So the reference angle is the size of the rotation from the x-axis to the terminal arm. So in this case, it's actually 1.373 radians. Now, it is in the negative direction, but I don't care about that when talking about the reference angle, which means that this one all the way over here is also 1.373 radians. But it's 1.373 radians less than, so if I'm kind of starting over here and I do a standard angle all the way to 180, which is pi, it's pi minus that amount because I'm backing up 1.373 radians. Now, 1769. Okay, so I'm going to cut that out because that was a struggle, but I'm going to leave the fact in that I struggled. So there you go. All right, now we're going to take this value and say this number is a value that's a positive it's in the positive rotation between 0 and 2 pi. So this is one of our two answers. The other answer is going to be the positive rotation that has the same terminal arm as negative 1.373. So I'm going to take that negative 1.373 and I'm going to add 3.1415 to that because I'm going to do times 2. I'm going to do a full rotation added onto it, so not pi, but 2 pi. And if I were to do that, I get approximately 4.910 radians. There might be a little bit of a rounding thing with that thousandths position, but I'm not too worried about it. So these would be our two answers for the value in the values of theta that exist for this particular tan theta is equal to -5 in one full rotation. So one of the most important things here is for you to either have your unit circle memorized and you can pull out the first one only if it's a special angle. From there, it's really important that you recognize for most trig equations that we're working on right now, there are going to be two answers. There's not two answers if you're at one of the extremes. So there's only one place, for instance, where you have a y value of +1 or a y value of -1 or an x value of +1 or an x value of -1, which is the same thing for your cosine sine ratios being equal to those amounts. But for all the ones that are between -1 and 1, we're going to end up with two locations where that is going to be okay within every single full rotation. So be sure you're comfortable with looking for that second one by using reference angles and pegging down the quadrants for which your statement that you started with would be true. Hopefully you found that one helpful. I know it was another long one, but if it was helpful, if you could like and subscribe, that would be great. Leave some comments, and as always, take care, folks.